following is an interesting problem. It can actually be thought of as a rolling problem. Suppose we have a disc like this with a string wrapped around the perimeter, and I release it from rest. Let's say we want to figure out the tension in the string as it falls and the acceleration of the center of mass. Okay, so we have a disc whose ICM is equal to 1/2 m r squared. Tension acts upward on the disc, and at the center of mass, the weight acts downward. If we use Newton's second law for translation, sigma F equals ma, you can see that the weight minus the tension is equal to the mass of the disc times the acceleration of the center of mass of the disc. Now let's use Newton's second law of rotation. Sigma tau equals I alpha. And I'm going to sum torques about this point P right here. So the net torque about P then would be the weight times the lever arm R, and that's equal to IP, which would be the moment of inertia about the center of mass, which is 1/2 mr squared for a disk, plus the mass of the disk times the times the perpendicular distance between this axis, the central axis, and the axis that runs through P squared. And then alpha would be ACM over R. As you can see, the R's cancel. So we have that the weight, which is mg, Newton's second law, is equal to 1/2 m plus m, that quantity times ACM. And 1/2 m plus m is 3/2 m. Mass cancels, so we see that the acceleration of the center of mass is going to be equal to 2/3 g. 2/3 g. How about the tension? Well, now that we know the acceleration of the center of mass, we can substitute that into here. So we have weight minus t is equal to m2 g over 3. Weight is mg. Solving for t, we get mg minus 2/3 mg, or that would be mg over 3, where the tension is equal to 1/3 the weight, which we're applying here. You know, it's interesting, if you think about it, this is just like the problem where we have a disc with a force applied at the axle. If you remember that problem, remember how the force of static friction ended up being to the left and was equal to 1/3 the force. Here the tension, right, is analogous to the friction, and the force that we apply to the axle of the disc is analogous to the weight. I'm going to use the spring scale to get the weight of the disc. So it looks like about 6 newtons. So if the theory is correct, the tension in the string that unravels as the disc falls should be 1/3 that, or about 2 newtons. Okay, so now I'm going to release the disc, and the spring scale should be able to measure the tension in the string as the disc falls. falls. So here we go. I'm going to hold this on the count of 3. 1, 2, 3. Let's take a look at this problem. We have a disc that is being pulled along a table by an unraveling string that comes off the top. And this end of the string goes around a pulley that's fixed to the table. And at this other end of the string, we have a hanging mass, M. Okay, the disc has a mass, capital M, radius R. Let's say we want to figure out the acceleration of the center of mass of the disc and the acceleration of the falling mass here. So I'm going to start out with Newton's second law of translation for the hanging mass here that's accelerating downward. So we have sigma F equals ma. So we would have the weight of this hanging mass, mg, minus the tension in the string, which of course would be less than the weight, equals m times the unknown n. Now, the tension in the string here should be equal to the tension in the string here, because the pulley, we're going to assume, has a moment of inertia that is practically 0. Therefore, these tensions should be equal to each other in magnitude. Now what I'm going to do is sum torques about the point of contact between the disc and the table. So sigma tau p is equal to IP alpha. So we have the tension in the string times the moment arm 2r is equal to the moment of inertia of the disc about its center of mass plus the mass of the disc times the perpendicular distance between the axis that runs through the center of mass of the disc and the axis at point P squared. Okay, that's the parallel axis theorem, times alpha, which is equal to the acceleration of the disc's center of mass divided by the radius of the disc. Now, what's the relationship between this acceleration and this acceleration? Well, this acceleration is the acceleration of the mass, which is the same as the acceleration of the string. So the top of the disc has this acceleration. But we learned previously that the acceleration at the top of the disc is equal to twice the acceleration of the disc's center of mass if the disc rolls without slipping. So ACM is equal to half of the falling mass's acceleration. Okay, this quantity here becomes 3/2 mr squared. So you notice that the r's cancel, so that leaves us a 2 times the tension is equal to 3/2 m a over 2. Or the acceleration of the falling mass we could solve for, although we don't know tension, but we can get tension by combining these two equations, I guess. So I'll tell you what, let's do this. Let's solve this equation for tension, substitute it into here, and then we should be able to solve for the acceleration of the falling mass. So let's take this equation, first solve it for tension. So we have T is equal to mg minus ma, and then substitute this expression into that equation. So that gives us 2 times the quantity mg minus ma equals 3/2 m a over 2. Now we need to solve that for a. But before we do that, can you see that the masses cancel? So we have 2g minus 2a equals 3a over 4. So we have 2a plus 3a over 4 equals 2g. So that's, let's see, 8 over 4a plus 3a over 4 equals 2g. or 11a over 4 equals 2g, or a is equal to 8g over 11. So the acceleration of this falling mass is 8g over 11. So to find the acceleration of the center of mass, then don't we simply take half of that acceleration? So the acceleration of the center of mass is equal to a over 2.